Over $10 billion is the enormous value generated annually by the global construction nail manufacturing industry. Unbelievable, right? A small, inexpensive, seemingly insignificant item found everywhere is actually a real gold mine. But have you ever wondered how, from rough rolls of steel wire, millions of sharp, uniform nails can be transformed in the blink of an eye? In today's video, let's take a peek inside a factory to explore the entire nail manufacturing process from A to Z. Each year, the world mines approximately 2.5 billion tons of iron ore. Almost all of it, about 98%, is used to produce steel, the material that makes the tiny nails we're discussing in this video. From these ore deposits deep underground, the raw material undergoes numerous processes such as crushing, sorting, iron smelting, steel making, and then being rolled and drawn into miles-long coils of steel wire before entering the nail-making process. Interestingly, after such a lengthy journey, the final stage takes place at an incredible speed. A modern high-speed nail-making machine can produce over 2,000 nails per minute. In an instant, the steel wire is fed into the machine, automatically cut to the correct length, stamped, and sharpened with very high precision, requiring almost no human intervention. And it's truly miraculous that a product weighing only a few grams originates from massive blocks of rock weighing tons. So, how is iron ore mined? The journey of a nail begins in massive iron ore mines. Before mining begins, engineers must drill exploratory wells to precisely determine the location, shape, and content of the ore body. Only areas of sufficiently high quality are put into operation, as the cost of establishing a mine can reach $5 billion. In open-pit mines, the overburden is removed to expose the iron ore beneath. Giant drills then create holes up to 50 feet deep, before explosives are loaded, according to a pre-calculated plan to efficiently break up the rock. After the blast, large hydraulic excavators load the ore onto dump trucks with a load capacity of over 400 short tons per trip for transport to the crushing plant. Depending on the distance, ore can be transported by dump trucks, conveyor belts, trains, or ships. At large mines in Australia and Brazil, ore trains are often over 1.8 miles long, pulling more than 250 wagons and capable of transporting over 30,000 short tons of ore in a single trip. Thanks to this large-scale transportation system, raw materials are continuously supplied to mills, ensuring that steelmaking lines can operate almost 24 hours a day without interruption. Upon arrival at the plant, iron ore is fed into a crushing system to reduce its size before mineral separation. First, a jaw crusher processes large rocks into smaller pieces. Then, the ore continues through a cone crusher or ball mill, where steel balls continuously impact and grind the ore into particles as small as 0.04 inches. Crushing the ore is only the first step. What the plant really needs is to separate the iron-containing mineral particles from the remaining soil, rocks, and impurities. That's why the ore is sent to the flotation stage. Here, the ore is mixed with water to form a slurry. Then a small amount of flotation reagent is added to alter the surface properties of the mineral particles. As air is continuously pumped into the flotation tank, millions of microscopic air bubbles are created. The target mineral particles adhere to the surface of the bubbles and gradually float to the surface, while most of the soil and rocks sink to the bottom. This mixture usually remains in the flotation tank for about 5 minutes before the mineral-rich foam layer is continuously scraped away for recovery. Thanks to the flotation process, the iron content in the concentrate can be increased from about 35% to over 65%, while most impurities are removed, creating a high-quality raw material. Although significantly enriched, the concentrate still contains a large amount of water, making it unsuitable for further processing. Therefore, the next step is dewatering using a filtration system. The concentrate mixture is pumped into pressure or vacuum filters, where the water is sucked or forced through filter cloths, while the iron ore particles are retained on the surface. In just a few minutes, the moisture content of the concentrate can be reduced to about 10%. In its fine powder form, the particles were too small and easily obstructed the flow of hot air inside the blast furnace. Therefore, the concentrate was mixed with a small amount of bentonite. The mixture was then fed into giant pelletizing discs over 20 feet in diameter. As the discs rotated continuously, the ore particles rolled and clung to each other, forming nearly spherical pellets about 0.5 inches in diameter, roughly the size of a marble. Interestingly, this shape wasn't for ease of transport, but rather to help distribute the hot air evenly during steelmaking, thereby improving the efficiency of the blast furnace. To become sufficiently hard for steelmaking, the ore pellets are placed in a furnace. Here, the temperature is raised to over 2,300 degrees Fahrenheit, enough to cause the ore particles to bond tightly together without melting them. During the heating process, each pellet shrinks by about 10%, becoming much denser and harder than its original size. After controlled cooling, a standard pellet can withstand a compressive force of over 550 pounds. This strength prevents them from breaking during transport and maintains their shape under the weight of thousands of other pellets inside the blast furnace. Once hard enough to withstand extreme heat and pressure, these ores are finally ready to enter the blast furnace. From the top of the furnace, iron ore is fed in layers along with coke and limestone. Meanwhile, air heated to about 2,000 degrees Fahrenheit is continuously blown in from the bottom of the furnace to burn coke. When moving to the bottom of the furnace, the temperature increases to nearly 2,800 degrees Fahrenheit, enough for iron to melt and accumulate into liquid iron, while limestone combines with impurities to form slag that floats to the surface. The interesting thing is that a modern blast furnace can operate continuously for more than 15 years without being turned off. After being molten, the material is still far from the shape of a nail. Instead of being poured into individual molds, the molten steel is fed into a continuous casting system, where it flows through water-cooled molds and solidifies into long steel billets. These billets are then cut to standard lengths before being transferred to a hot rolling line. Here, they are reheated to approximately 2,100 degrees Fahrenheit, and then pass through more than 20 consecutive rolling stands. Each time they pass through a pair of rolling mills, the cross-section of the billet shrinks until they become steel bars only about 0.22 inches in diameter. Upon exiting the line, they are coiled into coils weighing over 2 short tons, ready for wire drawing. However, this diameter is still too large for nail production. Therefore, the coils are further drawn through multiple carbide dies of progressively smaller diameters. After each drawing, the steel wire becomes longer, thinner, and stronger due to work hardening during processing. Only when the required diameter is reached is the steel wire coiled again and transferred to the nail-making machine, where the long journey from the iron ore finally comes to an end. Once the steel wire coil is of the correct size, the nail-making process truly begins. The coil is placed on a rotating stand and continuously fed into the nail-making machine. Because the wire is coiled after production, it must pass through 11 staggered straightening rollers to become almost completely straight. Next, the wire feeder pushes the steel wire forward to the preset length. Immediately afterward, a high-speed cutting blade cuts the wire into short segments, creating blanks of nearly identical size. Each freshly cut piece of steel wire is quickly shaped into a complete nail. First, one end of the workpiece is held fixed in a die, while a punch presses down hard on the other end to form the nail head. Instead of melting or welding additional metal, the machine utilizes the workpiece material itself, flattening it in a single stamping motion. Immediately afterward, two shaping blades bevel the other end to create a pointed tip, allowing the nail to easily penetrate wood or various other materials. From a straight piece of steel wire, the machine takes only a fraction of a second to complete both the nail head and the tip, with almost identical shapes. The newly formed nails are not yet ready for shipment. Before packaging, they are placed in a large rotating drum for cleaning and surface treatment. Inside the drum, the nails are mixed with sawdust or specialized polishing particles. As the drum rotates continuously, thousands of nails collide and rub against the material inside, removing small burrs, residual lubricant, and making the surface brighter and more uniform. Thanks to this method, tens of thousands of nails can be processed in a single batch. After surface treatment, the nails are sent to the inspection and packaging area. From here, the nails leave the factory for hardware stores, construction sites, and ultimately the homes, bridges, and familiar objects around us. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications so you never miss another journey inside the world's most fascinating factories. And let us know in the comments, what everyday product would you like us to take apart next?